Yes. Okay, thank you. Welcome to my talk. My name is Onno Eberhard. This is a joint work with Thorsten Zesch done at the Language Technology Lab at the University of Duisburg-Essen, and I'm going to talk about the effects of layer freezing on transferring a speech recognition system to under-resourced languages. Okay, as an introduction, most available automatic speech recognition systems are built for English. This is just because there's much more training data available for English than for any other language. But talking about other languages, the problem there is that we have less data, and this is a problem because then these large-scale models built for English can't easily be trained on a small amount of data because they will just overfit. And in this work specifically, we will look at German and on Swiss German data. So a solution to this would be to just use a smaller model. However, speech recognition is a very complex task, and these small models usually have a bad global optimum. So that's not a very good solution. And what is usually done is to use transfer learning. So that means we first train a large model on a related task with more available data. So in this case, that would be we train a ASR system on the English language, and then we freeze some of the parameters, which reduces the model complexity, and then we train it on the language you actually care about. So this is not new in this context. We actually only want to look at how the number of parameters that we freeze actually changes the outcome. So if we freeze more or less, yeah. Okay, we do this by looking at one specific ASR architecture, and namely the open source Mozilla Deep Speech, specifically version 0.7. Here's a small picture. So going from left to right here, this is meant to represent some audio data. And then what is done is we cut out a small piece of that data and extract some features and pass these features into a 6-layer deep neural network. The first 3 layers are just fully connected and ReLU activated layers. Then there's one LSTM layer, another fully connected ReLU activated layer, and then one fully connected layer, which is the same size as the alphabet of the text. So it's meant to output character probabilities over the alphabet, which includes some special characters like space or an apostrophe, and then there's a softmax function back here that produces a valid categorical distribution. So the input features that are extracted here before passing it into the network are mel frequency capture coefficients. Then the output, as I said, are character probabilities using a softmax function. The loss function is the connectionist temporal classification, which we optimize using the ADAM method. And we also use a language model back here. We could just use these character probabilities and maybe do beam search along those, but obviously using a language model improves results significantly because there are a lot of character combinations that are just very unlikely in a real language text. Okay, so back to transfer learning. How is this done in neural networks? Well, deep neural networks normally need a lot of data to perform well, if they are deep especially. And if not enough data is available, then transfer learning often helps, which is an alternative to just using a less flexible model, for example, by removing a few layers, as I already mentioned before. So what do? We first optimize the weights of a related pre-text task. This is called pre-training. So in computer vision, famously, many deep neural networks are pre-trained on an image classification task using the ImageNet dataset or on a self-supervised pre-text tasks. And this is meant to provide good features at the beginning, which then don't need to be learned when we only have a little training data for the task we actually care about. And in this case, of course, that would be to train a large model on the English language data. So the second step is then fine-tuning, where we use these optimized weights as a starting point. We don't randomly initialize weights anymore. We now use these optimized weights and then use those to learn the better weights for the task we actually care about. This pure transfer learning approach doesn't really prevent overfitting because the model capacity is still the same if we don't freeze any parameters. So that's what we normally do. We reduce the complexity by freezing some parameters of the model. And in deep learning, this is called layer freezing because we freeze complete layers one at a time. Okay, so the question now is, which layers should we freeze of the network? So the assumption we rely upon here is that the features learned by an early layer are more general than the transformations learned by a later layer. This has been shown to be the case in computer vision, where you've probably seen this. If you have a deep convolutional neural network, for example, for image classification, then the first few layers actually learn very simple filter functions like Gabor filters. And the later layers, you can see more complex features like eyes or faces or the like. There's less evidence for this hierarchical, for these hierarchical features in ASR, but there's also been less research. And what we do, we just assume this to be true and we freeze the earlier layers. So if we do this, if we freeze the earlier layers and then learn the later layers, we can think of a deep neural network to be composed of two parts, where the first part is the feature extractor, which is then assumed to be general over different languages. And the second part is the classifier. So in this case, actually a classifier multiclass over all of the letters in the alphabet. And we assume this part to be specific to the task. And then, of course, what we want to do is we freeze the feature extractor, which is general. We don't need to learn these weights anymore. We just learn the second part, the classifier. One problem still remains, which is that there's no really clear line between these two parts in a neural network. It's all just layers after layers. So we don't know how many layers we need to freeze, and that is what we experiment with in this work. I quickly want to go over the data sets that we use. Okay, so the pre-training is performed not by us. It's actually Mozilla trained their network, and we just downloaded the checkpoint. And they used a very large English language data set from many different sources, including LibriSpeech and Common Voice English. And it's definitely over 6,500 hours. I don't know how many hours exactly, but it's a large data set. Then for German language, we use Common Voice German, which consists of utterances between 3 to 5 seconds. And it is collected and reviewed by volunteers. So that means we have actually a lot of speakers, but it's overall not a very large data set. And the Swiss German data set is the German-Val 2020 data set, which consists of parliament speeches, and we have about 70 hours of speech in total. And the transcript, importantly, are in standard German, which then means for us that we can use the same language model for both languages, which we train on a few sources like Wikipedia. Okay, now what do we actually do? We do a few experiments. We do all of these for both the German and for the Swiss German dataset. Okay, first we just train the complete deep speech model from scratch, random weight initialization and node transfer, which we call the baseline model. Then the second thing we do is we train the model not by randomly initializing the weights, but by transferring the weights from the English pre-trained model. However, we don't do any layer freezing here. And then we vary the number of layers we freeze in the end. So we do one experiment where we freeze just the first layer, one where we freeze the first two, and then first three, first four, first five. We cannot freeze the sixth layer because of the different alphabet sizes of English and German. So we always have to reinitialize the sixth layer. And then we also do one experiment where we freeze 4 layers, but not the first 4, but the 5th instead of the 4th. And we do this because we thought maybe the LSTM encodes some kind of language-specific correlations over time, and maybe it's an advantage to not freeze this one, but instead freeze the 5th layer. And yeah, that's all the experiments we do. Again, once for the German and once for the Swiss German data. Okay, so here are our results. It's a lot of numbers. That's okay. First, on the left-hand side here, this is again just the different methods from the last slide. So we've got the baseline where we do no transfer learning, here where we transfer the weights but freeze no layers, and then here where we also transfer the weights and freeze a different number of layers. And then here on the top here, we have the German data and the Swiss German data with word error rate and character error rate. And if we just look at German first, then we see that the baseline model, where we just don't do any transfer learning, performs worse of all of these. So that's the largest error. Then if we transfer the weights but don't freeze any layers, this is definitely better than the baseline, but still worse than if we freeze layers. If we freeze 1 instead of 0 layers, we get a huge increase in performance. And then if we freeze more, it actually seems to not really make a large difference how many layers we freeze in the end. So the best results are here with freezing the first 2 or the first 3 layers, where we get about 44% word error rate. But freezing the first 4 or the first 5, it all works out pretty much equally. And this is really, we didn't really expect this, because if we freeze the first 5 layers, going back to this picture here, that means we freeze everything except for the last layer. And that basically means that we just train a linear classifier. So it's kind of a standard, it still performs rather well. And for Swiss German, here on the right side, results are similar. So here the baseline actually is a bit better than the 0 frozen layers, but both of them are still decidedly worse than all of the other experiments where we do freeze any amount of layers. Okay, and just to bring home this point that actually it seems to not make a huge difference how many layers we freeze. Here are the learning curves for the experiments. Let's just look at the left side first. That is the German data set. On the x-axis here is the epoch. So we always train for 30 epochs, but the best epochs were always in the first half. So we only plot the first 15 epochs here. And on the y-axis here, that's the loss function. And we can see that the baseline model performs not very good. So it's the best epoch here on this kind of loss. The 0 frozen layers in yellow is this one here, and it's a bit better for German than the baseline, but it's still not very good. And then all of the experiments where we freeze any number of layers, they look actually very, very similar. And maybe which one is better, which one is worse, it looks like it sometimes it's more noise than signal, what we observed there. And for the Swiss German data set here on the right, it's exactly the same plot. So the baseline version in blue and the 0 frozen layers version in yellow, they also look very similar, these curves. And again, all of the experiments where we freeze at least 1 layer, they all look very similar and are much better than all of the other ones. Okay, so to summarize, we see very similar results for German and for Swiss German data. We observed the best results with 2 to 3 frozen layers for both experiments, for both data sets. And the number of frozen layers seems to be unimportant as long as we freeze at least 1 layer. We observe a large difference between freezing 0 or 1 layers and freezing all layers except the last, which again means that it's actually just a linear classifier, yields very good results still. And we don't observe any difference between freezing the LSTM or a normal layer, which again was this one experiment. And the results, go back there, they are very similar. So this one is where we freeze just the first 4 layers, including the LSTM. And this one is where we skip the 4th, which is the LSTM layer, and then freeze the 5th instead. So both of these are 4 frozen layers. Both for German as well as for Swiss German, the results do look very similar. So it doesn't seem to make much of a difference. Okay, so what does this mean now? So it seems to indicate that the features learned by one language, so in this case, English, are indeed general enough to apply to other languages as well. And as we observed, this is even general enough to provide good features for a linear classifier. And the takeaway would be now, just if you do this kind of experiment, don't really worry about the number of frozen layers as a hyperparameter. It seems to be not very important. And open maybe still is if this would also work if we froze the last layers instead of the first layer, which would kind of like break this dichotomy of first you have a feature extractor and then we have a classifier. Or maybe it wouldn't break it, or we say, would it also work if we train the feature extractor on the new language and keep the classifier? Would this also work? And also would it just work if we just use any random subset of parameters with the same degrees of freedom? Yeah. Oh, and lastly, I just want to mention a few limitations of this work. So we only looked at very closely related languages here. So the original language was English, and then we transferred to German or to Swiss German. These are closely related. They maybe don't sound very similar. So it's not obvious from the start that the features learned for English would also work well for the other two languages, but they are still closely related. And if we were to look at other languages, for example, tonal languages like Mandarin or Thai, or maybe languages which heavily use phonemes that are very rare or even non-existent in English, or any other kind of different language, maybe the features learned by this English language system would not be enough to transfer well. Yeah, okay, and now I'm at the end of the talk, so I guess if there are any questions, now would be the time.